So, today we will discuss the criteria for convergent and diverging sequences. We have already seen that if x n be a sequence of real numbers, then it is said to be a monotone if there is a sequence of the positive integer in increasing order or decreasing order, such that the corresponding terms of the sequence x n 1, x 2, x n n, then they form the monotonic sequence. X n 1 is less than x n 2, less than x n 3, and monotonic increasing, or if it is reverse, then we say monotonic decreasing. And also, if a monotonic sequence which is bounded above or below, it must be a convergent sequence. So, based on this, we have seen that sequences, if you are monotone and bounded, we can say that sequence will definitely converge. But every sequence need not be a monotone sequence, because there are also sequences which are not at all monotone sequence. Then how to find out whether the sequence is convergent or diverging? So, for this we have certain results which will directly tell, without computing the limit, whether the sequence is convergent or not. And one of them, which is very important result, is given by the Cauchy, which is known as the Cauchy convergence criteria for a sequence of real or complex numbers. Okay. So, let us see, the first thing is that if a sequence is convergent, then all of its subsequences will also converge to the limit. We know if a sequence is convergent, then the limit is unique. This we know, that as limit of a convergent sequence, we know a limit of a convergent sequence is unique. That is, if there are two limits, if suppose if x dash and x be the two limits of a convergent sequence, x n of real numbers, then x dash must be equal to x. The reason is, if we start with x dash minus x, then this can be written as x dash minus x n plus x n minus x. Now, since x n converges to x dash, it is a limit. So, by definition of the limit, for a given epsilon greater than 0, for given epsilon greater than 0, there exists an integer, positive integer capital N 1, such that mod of x n minus x dash is less than epsilon by 2, say, for all n greater than equal to n 1. Similarly, for the same epsilon greater than 0, there exists a positive integer, say n 2, such that mod of x n minus x remains less than epsilon by 2 for all n greater than equal to n 2. So, if we choose capital N to be the maximum of n 1 and n 2, then this result is also true for n greater than capital N. This is also true for n greater than capital N. Therefore, this thing can be made less than epsilon by 2 plus epsilon by 2 for n greater than n. So, this shows that x dash must be equal to x. That is, a limit of the convergent sequence is always unique. So, it means if a sequence which has a different limits, it cannot be a convergent sequence. So, this is the one of the criteria you can say, that if a given sequence is there, find out the limits. If along various path it has a different limits, then the sequence will not be a convergent sequence. Then we call it such a sequence, of course, a diverging sequence, which you all know. Another thing is, if a sequence is a convergent sequence, then all of its subsequences will also have the same limit. So, that is very interesting result, which is not true in case of the divergent sequence. divergent sequence, the subsequences have different limits. Okay. So, if a sequence x, which is say x n of real numbers, converges to a real number, say x, then any subsequence x dash, which is say x n k of x, also converges to x. So, if x n is a convergent sequence of real number, then all of its subsequences will also converge to x. Subsequences we mean, we have discussed there that if x n is a convergent x n is any sequence, and if we identify these integers n 1 n 2 n n such that which are increasing or decreasing order, then this sequence x n k means increasing order, n 1 is less than n 2 n 3, then this sequence will be a subsequence. So, this will, now let us see proof. Proof is very simple. What is given is the sequence is a convergent sequence. So, it is given the sequence x n, which is denoted by say x, is a convergent sequence. So, for the given epsilon, by definition, for given any epsilon greater than 0, a positive number, there exists an positive integer, say capital N, which depends on say epsilon, such that mod of x n minus x is less than say epsilon for all n greater than equal to n depends on epsilon. Okay. This is what we get. Now, we wanted any subsequence must converge. So, let us pick up the terms. Take n 1 less than n 2 less than n 3 less than n k, and like this. This is the sequence of increasing sequence of natural number, increasing sequence of positive integers, okay. n 1 is less than n 2 n less than n 3 positive integer. Now, obviously, clearly this n k will be greater than k for any, because k is 1, then you can identify n 1 which is greater than 1, then k is 2, you can identify another integer positive in 2 such that n 1 is less than n 2 which is greater than 2, and like this. So, it is very easy to verify that this is follows. Okay. Now, if this k is greater than this number here capital K n, if this number is capital N, so what we do, hence if this k which we have taken is greater than equal to capital N, which depends on epsilon, then obviously n k will also greater than k. So, for all n k's greater, so n k will also be greater than k, which is greater than equal to n depends on epsilon. Therefore, for these n k's, this result is true. So, we get mod of x n k minus x is less than epsilon for all n k for all k belongs to the natural number n. For all k belongs to n. This is true, but n1 n2 n satisfy these conditions also which we have shown. Therefore, the sequence subsequence x and k will converge to x. So, this implies that the subsequence x and k, this subsequence will converge to x, and this is an arbitrary sequence we are choosing. So, any subsequence of x will definitely converge. So, if a sequence x n is a convergent sequence, then all of its subsequences will converge. So, this is one. Now, let us suppose we have a converse part of it, the criteria where the limit fails, then it will lead to a sequence which is a diverging sequence. Okay. So, let us find out what will be the corresponding or equivalent condition when the sequence does not converge. Okay. So, let us see the criteria or the divergence of this sequence. If sequence x n or limit of x n when n tends to infinity does not converge to x, does not converge to x, or the limit fails, then what will be the, then we have the following equivalent criteria. Then we have this theorem will help you in identifying the diverging sequence, the criteria for diverging sequence. So, let x, which is x n, be a sequence of real number. Real numbers. Then the following conditions, are equivalent. The first condition is the sequence x which is denoted by x n, x n does not converge to x in real, means does not converge to a number x. The second criteria is there exists an positive epsilon naught greater than 0 such that for any k belongs to n, n is the natural number, this is the set of natural number n. For any k belongs to n, there exists n k, a positive integer belonging to n, such that n k is greater than equal to k and mod of x n k minus x is greater than equal to epsilon naught. And third condition is there exists an epsilon naught greater than 0 and a subsequence x dash, say x of x n k of x such that x n k minus x is greater than equal to epsilon naught for all k belongs to n. Okay. So, what this shows is proof we will see x n is a sequence of real number, then the following conditions are equivalent. The sequence x n does not converge to x, then it is equivalent to this, equivalent to this. Basically, the difference between second and third is, second says that n case which does not follow the increasing order, may or may not follow the increasing order, that just there exists some n k where this is true, but here there must be a sequence n 1 n 2 n n which should be a increasing order n 1 less than n 2 less than n 3, and corresponding to this positive integer a sequence x n k can be obtained, so that it satisfies this condition. Now, what is this condition? When we say the limit of this x n is x naught or is x, it means if I draw a neighborhood around the point f, this with a suitable radius say epsilon naught, with a suitable radius epsilon naught, then all the terms of the sequence must fall within this if the limit exists. But if the limit does not exist, it means all the terms of the sequence after certain stage will fall somewhere outside of this neighborhood, because this also shows that if x is if you draw a neighborhood around the point x with a radius epsilon naught, then all the terms of the sequence after this integer, say n 1 is n 1 x n 2 etc., this will not satisfy, this will not fall within this region, it will fall outside of it. So, this shows the criteria for this shows the sequence x n does not have a limit. Okay. So, we will go to the proof that how these three conditions are equivalent. Means we can, if the sequence does not converge, we can immediately say this condition holds, that is there exists a epsilon naught and a subsequence such that the x n most of the terms or infinitely many terms lies outside of the epsilon neighborhood, epsilon naught neighborhood of x. Okay. Let us see the proof of this. Okay. So, first is very first implies 2, 1 implies 2. Let us see what is the first. Sequence does not converge, then we have to find out this thing. Okay. So, if the sequence does not converge, given the sequence x n does not converge to x. It means what? It means for the convergence, for any epsilon greater than 0, there will be an n such k such that all n greater than a difference in length, but if it does not converge. So, we can identify a epsilon naught, and corresponding to the epsilon naught we can identify the sequence where it violates the condition of the neighborhood that. So, then for some epsilon naught greater than 0, for some epsilon naught greater than 0, it is impossible to find a natural number, find a positive integer or find a positive integer say k such that for all n belongs to a natural number capital N. This is a set of natural numbers, belongs to capital N such that for all k, such that for all n greater than a, the terms x n satisfy the condition satisfy mod of x n minus x is less than epsilon naught. So, what he says is, if suppose does not converge, it means for at least for some epsilon naught, it is impossible to find an integer k such that when you choose all n for all n greater than equal to k. This condition will not satisfy it. It is impossible to satisfy this condition. That is to say, this means that for each k belongs to n, it is not true that for all n greater than equal to k, the inequality mod x n minus x less than epsilon naught hold. For this holds. That is the same thing for each k. It is not. What do you mean? It means we can identify a sequence. We can identify a natural number n k such that which n k is greater than k and this condition violates. That is, in other words, we can say that for each k belongs to capital N, there exists a natural number or positive integer, you can say n k, which is greater than or equal to k, such that mod of x n k minus x is greater than or equal to epsilon naught. That is what here, because if does not converge means this condition will satisfy, because it is impossible to find out n k which will follow this condition. So, there must be a n k, some integer can be obtained which will violate this condition. So, that is what you get. So, 1 implies 2. Now, 2 implies 3. It follows immediately. Second condition said that there exists an epsilon naught such that for any k there exists n k such that n k is greater than equal to k. Now, you can find out n 1 which is greater than 1 and satisfying this condition. Then n 2 which is greater than n 1 and greater than this will satisfy. So, using this given 2. Okay. Then let n 1 is a integer, is a natural number be such that n 1 is greater than equal to 1 and it violates, it satisfies this x n 1 minus x is greater than equal to epsilon naught. Then you choose n 2 which is greater than n 1 and again it satisfies this condition is greater than equal to epsilon. So, continue this way. So, continue, once you continue you will get a sequence n k. So, continue this, way, we can find a sequence n k of positive integers such that x n k minus x naught is greater than equal to epsilon naught for all k belongs to n. Where what is n k? Where this condition is satisfied, where n k is greater than n k minus 1 and so on is greater than n 1 which is greater than equal to k 1, okay, like this. So, we can identify this sequence, clear, and this shows what? This shows that the condition third is valid, equivalent. Okay. So, third implies first. Given this condition holds, that is there exists an epsilon naught and a subsequence x dash n. So, and a subsequent x dash. So, we can say subsequence x Should I write this way? Yeah, this was the third condition. There exists x y naught and a subsequence x dash n such that this condition holds. So, here this is given. We want the x n does not converge. Okay. So, suppose the sequence x, here you can say in this the subsequence, we can say that there exists we get a subsequence x dash which is x n k of x such that this condition violates, that is all. Okay. So, this condition is, suppose sequence x n converges, suppose the sequence x which is x n has a subsequence x dash n x n k satisfies condition 3. Okay. So, once it is there, then we have to show, required to prove the sequence x which is x n does not converge. This we wanted to show. Suppose it is not true. Suppose the sequence x which is x n converges. Okay. Suppose it converges. Now, x dash, since x dash which is x n k is a subsequence, of x, and this sequence we have assumed to be convergent. So, all of its subsequence must be convergent, okay, by the just previous row. So, this implies the sequence x n k, this sequence must converge to x, or converges to x. It means that is mod of x n k minus x is less than equal to epsilon for all n, or for all k belongs to n. If it is convergent, or for all n, you just say x n minus a for all n greater than equal to capital K belongs to. Okay. But that will violate this condition, because the condition said x n k minus x naught is greater than epsilon naught. So, for this particular epsilon equal to epsilon naught, but for epsilon equal to epsilon naught, we get x n minus x is not equal to less than epsilon naught. It is greater than or equal to epsilon naught. So, this is violates that condition. Therefore, this is a contradiction of our given condition 3. So, contradicts condition 3, because if it is suppose assumed convergent, then it must satisfy this condition, that x minus x n k for all k belongs to n, this must satisfy condition, but for this particular epsilon naught, this condition is violated, because this is this condition is not satisfied, because it is greater than epsilon. Therefore, contradicts the condition 3, and contradiction is because of a wrong assumption sequence converges. Therefore, this implies the sequence x which is x n does not converge, and that proves the result. Okay.